Thank you. So, hello, Insomniac. It's really great having you all here today. It's really great to be here today. So today we'll talk about Inglourious drivers, the less glorious drivers that exist out there. And for those of you who already managed to detect a typo in my slide, so congrats. There probably might be more in other slides. Those are not intended, but this one is. So basically, it's an homage to the great movie of Quentin Tarantino, Inglourious Bastards, which just used the same typo. Unfortunately, we are not here to talk about movies, right? We're here to talk about kernel drivers, so let's begin. My name is Omer Tsarfati. I'm a senior security researcher at CyberArk Labs. I'm doing security research for more than 8 years, something like this. In my spare time, I like playing basketball. When I'm not doing that, probably I will play some video games. And when I'm not doing that, I do some research for my own pleasure then. All right. So today we'll talk about a few things. So at the very beginning, we'll talk about the Windows driver framework. Right after that, we'll talk about some common mistakes that driver developers tend to do. And then we'll talk about one specific driver that created a really big mess and for some reason is widely used by a lot of vendors. Right after that, we'll talk how we managed to utilize VirusTotal for finding even more vulnerabilities than we found in the research that we conducted. And at the very end, we'll talk about some mitigations to the vulnerabilities we found and how you guys can mitigate most of them with one simple trick. Right, so before we start talking about the Windows driver framework, I want to tell you a short story. So a few years ago, I made a decision, maybe not the best decision that I ever made, but it was a decision. And I went to the store and I bought myself a gaming laptop. So I got this gaming laptop manufactured by MSI. And as some of you may know, the most important thing when you're playing video games on your computer, it's not about the graphics, it's not about the whole experience of the game, it's more about FPS. So basically, the more frames you have, the more fun you will have eventually. So there are a lot of ways to achieve FPS. One excellent way is to ensure that your cooling system is good and everything will stay chill. Unfortunately, gaming laptop suffers from overheating. So basically, you need to set your fans to their max most of the time. Another way to solve this problem, you can just add a nice spoiler to your rig. It might also help. I don't know about that, but it might. Right. So MSI was kind enough to develop this program called Dragon Center, which allows you to control a lot of things around your computer. And one of them is the cooling fans. But there is one thing about that. I don't really like its GUI. So I wanted to create my own program that controlled the cooling fans. And before I started to write any code, I started thinking which component in the system controls the cooling fan speed and how everything works around it. So basically, I thought that it's a user mode program application which talks to a low-level kernel driver. And before we're talking about user mode application communicate with kernel drivers, we need, at least in all operation system and specifically in Windows, we need to talk about privilege level architecture. So in Windows, we have 4 different levels of privilege, 4 different privilege levels. So the lowest one is the sandbox process, which there are not a lot of processes runs in as a sandbox process, mainly your browser, Teams, Slack, Discord, stuff like this. And we have the non-admin processes, which most of your program on your computer runs as. And then we have the services and the admin processes, which are considered to be a privilege level, which means that if an attacker runs in as an admin process or as a service, probably your computer is could be ultimately taken over. And at last but not least, we have the OS kernel, which includes also the kernel drivers. So some of those kernel drivers interact with hardware, and one of them might interact with the cooling fans. So basically, MSI needed to develop kernel driver that interact with the cooling fans. But when one developing a kernel driver, it actually takes a lot of risk and also a lot of responsibility for this. So that's because you are part of the kernel. So all the drivers just share the same system address space and essentially are part of the kernel. Fortunately, nowadays they all need to be signed, so there is a mitigation for that. You can disable it, don't do that. Also, you need to be in admin privileges, so yeah, this is a good thing. And don't screw up, because you're talking to hardware, you're filtering stuff. If you're not handling thing correctly, you will just crash the system, and this is not a good thing to do, at least if you are a developer. If you're an attacker, do whatever you want. All right, so here we are as security researchers, right? So from a security perspective, when we are talking about drivers, we want to know two main things. We would like to know which access we have to the driver, so do I have access to talk with the driver, and what are my permissions, and how do I communicate with the driver, and how does the driver actually parse data that I'm sending to it. So let's talk about access. In Windows, in order to interact with the driver needs to create a device. So the driver creates a device object and should specify which user can access it. So this is actually done by using a security descriptor, which can be located either in the INF file that comes along with the driver or in the driver entry. And this is set by calling IOCreateDeviceSecure. So as you can already understand, there is also a function called IOCreateDevice, not secure. Basically, what's going to happen when you will call this one, so the default security descriptor will be applied, and basically it means most of the users on the system can interact with the device. So in order to make sure also the device object accessible from user space, you need to create a symbolic link. And this can be done by calling IOCreateSymbolicLink or IORegisterDeviceInterface. Then the user or the user application or the driver needs to call createFile or anti-createFile to have a handle to the device. So here we can see a driver called vidsys exposing a device object called videxo. You probably can't see anything, so let's do a quick zoom. Yeah. All right, so on the left-hand side, we can see the driver object and all the devices it exposes to the object manager, and magic. On the right-hand side, we can see the groups and the users that have access to the device and what they can actually do with the device. All right, so let's talk about communication. So the driver register need to register dispatch routines through using the major function. Basically it means which operation the driver supports. So there are about 27 different major functions that exist. Most of them are not commonly in use. Mainly those 5 are in use commonly. So you have the create, close, read, write, and device IO control, which is, we'll talk about it later, is the most important one for us. All right, so this is how a driver entry will look like. So driver entry, it's like your main function of the driver. We can see here there is a call to IOCreateDevice, which will create a device called test.drv, and after that there is the registration of the major function, as I told you before, the most important one, the IRP MJ device control, which most of the interesting logic exists in, at least for our needs. All right, so just like in network packets, we also here have also packets, but little different packets. So those packets called IO request packets, or IRP for short. So IRP contains any of the dispatch routine would ever need. So the IRP structure is generated by the IO manager, and it consists of stack location, which is where all the important members reside. We have the request mode. We initiate the call, if it's the kernel, if it's the user land, the input and the output buffers sent to the driver, and the IO status information, which indicates how many bytes should be written back to the output buffer. Any misuse of those fields would probably cause a bug. So you might crash the system, you might allow arbitrary read, write in the kernel. So this is bad. All right, so besides that, the IRP struct also contains a field called IO control code, or IOCTL for short. So the IOCTL is it's a number that's used as an identifier for other programs to execute specific logic in the driver. So the IOCTL is just a function identifier, right? So it's basically packing a little bit more than that. So it's a 32-bit packed structure. So the first 2 bits indicates what is the transfer type of the request that's sent, and the 13 and the 14 indicates the required access of the request. All right, so let's talk about the required access. So it actually describes the required permission to send to the device IO control request. It's based on your permission when you called anti-create file or create file. So it depends on the handle you have. So there are about 4 different options: file any access, file read access, file write access, and file read and write access. So those are actually in order from the least privileged one to the most privileged one. Also, we have the transfer type. So this actually describes how the IO manager treats the user data. So here we have a lot of different nuances that the driver developer must know. And when there are a lot of different nuances you need to know, you should know there might be a lot of bugs. So there are 4 different options here. We have the method buffered, method indirect, method outdirect, and method neither. So here it's also in order from the most secure one, that is commonly considered to be the most secure one, to the least secure one. So method neither, as one of my colleagues call it, the mother of all evil. So yeah. All right, so in order to send a device control request, we will use the device IO control function, which takes a handle to the device. It takes a IO control code and the input buffer and its size and the output buffer and its size. Right, so by now, we know a lot and we know how to interact with drivers in Windows. So let's talk about mistakes. All right, so let's talk about method neither. So in this case, the IO manager is actually pretty much lazy. So the buffers and the lengths will reside in user mode, and the kernel doesn't copy them to the kernel space. They can be paged out, and it can cause some problems. The input buffer will be type 3 input buffer. The output buffer will be the user buffer. So the user can allocate and deallocate the buffers, making those pages invalid. So you need to be cautious when dealing with them. And also you need to know that every access to the buffers must be in a try except block. Also, you need to do some probing. So whenever you want to read or write to the buffers, you need to use probe for read and probe for write accordingly. But if you don't do them or you don't use them correctly, it will throw some errors on invalid address. So the call actually, if it's not in try except block, will crash the system. If the length is 0 of the buffer that is sent by the user, so actually those probing do nothing, and the validation just passed away, just passes. So if you're not probing correctly the kernel reads and the kernel reads from the buffer, you will crash the system at the very least. And well, at least for us as security researchers, you might have some info leak. And if you're doing it for writing, you will crash either crash the system or allow arbitrary kernel write. Right. So this is an example of a buggy code from a real driver. Here we can see that the driver developers didn't hear about probing. So in the first box, the driver reads in the input buffer. We see there is no probing function before the usage. In the second box, there is a dereference of a pointer without checking if the buffer is null. So this also might crash the system. On the third box, the address could already be paged out, causing a crash when writing to the output buffer. And besides that, the input and the output buffers access not in a try except block, try catch block, so the driver can get access denied and crash the system. And also in the second box, just like in the second box, also in the fourth box, there is accessing to the input buffer without any validation. And lastly, it's not in the box, but the access to the output buffer doesn't involve probing, which will eventually allow us to do arbitrary kernel write, memory write. So yeah, this is also a problem. Let's talk about the better brother in the family, the method buffered. So method buffered, in this case, the IO manager copies the buffers and the lengths to the kernel in a secure manner. So therefore, so those are resides in kernel memory, not in user space memory. You don't need to probe anything, so this is good. But you have to remember, if there's any fields that are embedded in the buffer, you need to treat them properly. So you need to do validations when you're accessing those. In this case, the input buffer and the output buffer will be the system buffer as part of the IRP structure. And also we have the IO status information, which actually, as I told you before, indicates how many bytes should be copied to the user's output buffer. If the IO status information is bigger than the input buffer length and the output buffer length is bigger than the input buffer length, the rest of the system buffer will be copied to the output buffer, will be uninitialized memory, and this could lead to info leak or crashing the system. So let's say we have one page of the output buffer length, it's 1 page, the input buffer length, it's 8 bytes, and the IO status information will be output buffer length, so we will leak about 1 page of memory from the kernel to the user space. Right, so here we have also an example to method buffer, to a driver implements IOCTL for method buffer. Again, it's not safe to assume that this code is bug-free. Of course, it's not if it's in the presentation. All right, so on the second box, we can see a nice length check, and beneath that check, they initialize some memory. After that, there is a if-else statement. If we fail to go into the first if statement, we'll go to the else, and in the else there is a status information with a really big number, around 11K of kernel memory that could be leaked, and in this case we'll just have a huge memory leak, or we'll crash the system if we'll get into an invalid page. Right, let's talk about direct IO. So in this case, we have two different methods. So we have method indirect and method IO direct. So in this case, there are two buffers that send into the kernel. So we have the system buffer and the MDL address. The second buffer is a direct buffer, which always will be paged in. So faster access for us, and this buffer can be used either for input or output. A kernel driver can also create MDL by using IOCreateMDL, followed by locking it with mmprobe locks pages, which is quite important. We'll talk a little bit about that in the next slide. And if this function fails for some reason, so let's assume that you gave it an invalid page, so it will throw an exception, and if this one is not handled properly, you will crash the system. All right, so you might ask yourself, what is MDL? So MDL is a structure that describes the fixed physical memory location that comprise a contiguous data buffer in virtual memory, or in simpler words. So the MDL actually describes a data buffer in a fixed position in physical memory, which will be always paged in and locked in memory. So it basically double mapping, one for the user and one for the kernel. Let's see an example of not writing a good code with IO, with direct IO. So in this case, we can see in the red box, we have a full control over the MDL with so there is a variable which an original name, controllable virtual address. In here we can see that there is a call to mmprobe and lock pages, which is not wrapped in try except block. And if we will send an invalid virtual address, we will trigger a BSOD and we will actually crash the system. All right. So we talked a lot about mistakes the driver developers do. We also I also showed you some examples. Let's get back to the MSI thing. All right, so so back to my laptop. I try to find the driver that Dragon Center interacts with. Lucky me, I found the one that it interacts with. It's WinIO, which is loaded by the Dragon Center service. And I check if I have access to the device it exposes. And fortunately, I do have access to interact with it. So I open IDA and started doing some reverse engineering. All right, so here is the decompiled code of the dispatch routine. Here we can see here we can see the system buffer, which is the buffer sent by the user to the driver. and its length. And here we can see there is a switch case with dioctals. Switch case goes over the different major function, and there's also another switch case embedded in it, which goes over the different ioctal that the driver supports. And for those of you who managed to see line 47, you might already found the bug. So in line 47, there is a mem copy from the user buffer with a controllable length to a local variable. So it actually means there is a potential buffer overflow here, right? So yeah, if we will send a buffer in the size of 32x plus 8, we maybe would be able to overrun the return address, right? And this is what we did. So we send a buffer and we crash the system. So basically we override the return address and we manage to run code in the kernel. You're probably asking yourself, hold on, isn't there any stack canary there that would prevent this? So they didn't compile the driver with stack canary, and this is bad. Don't do that. Use stack canaries. All right, so don't worry. It's not the only bug that exists in the driver. Basically, there are also the driver also loads low-level processes to read from I/O ports and read to I/O ports, and also it lets you to all right, and also it lets you to unmap and map physical memory into virtual addresses. So basically, you can read the whole memory. So this driver was a really buggy one. I didn't find what I wanted to find, how I controlled the cooling fans, but I found a lot of bugs. So this is a lot of process, but wait, there is more. So as I told you before, as a gamer, I want as much FPS in games as I can get. And only real gamers know that RGB gives you more FPS. So I made another decision. Again, not the best decision, but it is a decision. And I went to the store and bought myself a gaming keyboard manufactured by Razer. All right, so Razer was also kind enough to develop a program called Razer Synapse, which lets you control the RGB lights on your computer and stuff. And of course, as a good gaming program, it's also have its own drivers. So there is a driver that the Razer Synapse service loads called R0 Razer Synapse Service, original, and it exposes a device object named WinRing0. Right. So just like before, I located the driver file and started doing some reverse engineering. So let's jump into the code. So here we also have the main dispatch routine. We'll go to the device control function. So fortunately here, we can see that the driver developers did something different. They did some validation over the buffer length. So this is good, right? So we won't find any buffer overflows here, unfortunately. Yet, there are still some vulnerabilities in this as well. So here we have IO port read and write primitives just as before. And also, we got this thing. So this is actually interesting because the driver lets us to read and write to arbitrary MSRs. All right, so at this point you might ask yourself what MSRs are. All right, so MSRs are model-specific registers. So it's basically any various control registers in x86 instruction set used for debugging, program execution tracing, computer performance monitoring, toggling certain CPU features, and there is MSR called IA32L star, which holds the pointer to the system call handler, which upon syscalls, this pointer is loaded into IRP. And as you can already understand, if we will overwrite this specific MSR with arbitrary pointer to whatever we want, we will achieve arbitrary code execution in kernel context. So this is this is not good for the developers. For us, it's great. All right, so, but we didn't do one thing. We didn't check if we have access to the device object. So let's jump into the driver entry. to the IO create device. So as I told you, the IO create device, it's the not secured one, which will create a device with a default security descriptor. So in this case, it means that we will have access to the device and we will be able to trigger this vulnerability. So previous escalation confirmed. Or is it? When we went to the device object properties, we looked at the security that apply to the device, and we can see that only administrators and system can interact with that. So we can see a clear inconsistency between the driver code and the device security object. So the driver doesn't enforce any security descriptor. So the only logical explanation for this phenomena is that some other process just changes the device object security. All right, so basically it will look something like this. So we have the WinRing0 driver loaded, then the WinRing0 creates a device with the default security descriptor, then some random process just changes the security descriptor, and here we are. Yeah, but there is a small time gap between the creation of the device object and the time that some random process just changes the security descriptor. So there is a race condition there. And as attackers or security researchers, we can actually abuse this one. This is true as long as we are managed to run our code before the random process runs its code. Yeah, so basically after doing some research, some further research, we get into this one. So Razor Synapse Service uses an open source project called Libra Hardware Monitor Lib, which loads the WinRing0 driver. Then the WinRing0 creates a device object, and there is the rest condition, and some random process changes the device security descriptor. Fortunately, the Libra Hardware Monitor Lib, it's an open source project, so we quite easily could find its source code. So let's see what this one does. Right, so here we can see the DLL actually open handle to the service manager and creates a new service, or in other words, in this case, creates a new driver. And then it's asked the service manager to load the driver. Right after that, it opens an handle to the created device. Yep. All right. All right. So right after that, it opens handle to the created device and changes the security descriptor. Right. That's cool. Unfortunately, this service runs way before us. So basically, we won't be able to win this race condition. As far as I know, we need only to restore the driver in order to restore the service in order to achieve to win this race condition. Yeah, so this is bad. But they still want to find a way to exploit this vulnerability, right? So in order to restart the service, you need to be admin or in a privilege level, or you can just trigger an update. So basically, when there are updates, the Razor Synapse program commit an update, everything shuts down. So all the Razor Synapse services and all the other stuff that comes with it just closes. The update is triggering, and then you can actually create a race condition. Unfortunately, updates happens once in a month, twice. Like once in 2 months, so this is not good for us. We want to trigger it upon our request, right? So we found that we can abuse the plugin mechanism to trigger a update-like scenario. So yeah, basically Razor lets you to install 3 plugins, maybe more, and we whenever you install a plugin, so it will consider as an update, everything will shut down, and then we can trigger the race condition. Another fun fact about the source code: there is a to-do which replace with call to IO create device secure and driver. They didn't do that until today, so yeah. All right. So this is how the flow looks like. So we will write our POC exe. It will ask a Razor service to install the plugin. A Razor GMS service will initiate an update-like scenario, which shut everything down. WinRing0 will be unloaded. then it will be reloaded and it will create an object with a default security descriptor. We have our race condition there, and then the DLL will change the device security descriptor. All right, so let's see a demo. Cool, so here we have the Razor Synapse. All right, so here we can see all the plugins you can install. We will install the Alexa plugin, for example. Yeah, we run as low privilege user without that many privileges, unfortunately. We will run our exploit. So now actually we downloading the Alexa plugin. After it finished downloading, we will send a message to the GMS service to install the plugin. Here we can see that everything shuts down. The service is unloaded and deleted. Now it's reloaded, and we will try to open handle to it. We managed to open handle. We abuse the MSR IA32 to run code, and we managed to change our permission into system or application token. Thanks. Right. So let's talk about aggregation. So basically, we use VirusTotal to find even more vulnerabilities. Most of the time, you will use VirusTotal to hunt for malwares. So we came up with an idea to find similar vulnerable drivers, because the one that MSI used is really similar to the one that Razor actually is using. So we thought that there might be more. So we wrote a simple retrohunt job query that includes some debug strings from the driver, and we found 114 drivers that exist out there that too many vendors actually using those. We are talking about ASRock, MSI, Razer, Asus, Patriot Memory, Galax, Gigabyte, and much more. Yeah, so this actually was really nice to find even more vulnerable drivers by just using VirusTotal. Yeah, it always handy to find vulnerabilities by VirusTotal. All right, so let's talk about mitigations. So interestingly, just by having Hyper-V enabled on your system, you can mitigate some of the risks we talked about. So hypervisors, by design, can intercept any modification action initiated by the OS kernel. And Hyper-V, by default, prevents any modification to IA32L star, because it doesn't make sense that you will want to change this one. As long as you're a legitimate user, if you're an attacker. So yeah, you might want to do that, but Hyper-V won't let you. Unfortunately, Hyper-V can do that much and won't protect you from buffer overflows and stuff like this. All right. So, is this problem is fixed? Sadly, only partially. The kernel driver is still there, and it's actually still being used by different vendors. I don't know why, but it still happens. As an end user, I will recommend you to enable Hyper-V on the system and use antivirus that blocks malicious drivers. So some of those drivers are considered to be malicious nowadays. As a developer, please don't use the WinIO codebase, and neither any of the different variation like WinRing0, Antilib, MSIO64, and etc. And if you do, please fix the embedded security issues that there. Yeah, right. So we got some CVEs during the research. We also wrote a blog post about that. The QR code will be also in the next slide if you want to scan it. So yeah, thank you very much. I'm Omer Tsarfati. I had a great time presenting this talk to you, and feel free to contact me via Twitter for any questions, and I'm also around here. Thank you. Do you have any question? Yep. Might get you the microphone.
Thanks for the great talk. So you have said that the hypervisor intercepts the writes to the MSRs, but does it do it for all the MSRs?
No, actually, so basically it can catch every MSR change, but it treats different MSRs, like whenever it needs to block the change, it will. Whenever it just need to pass it along.
So is there still potential that maybe some other MSRs would actually allow you to like exploit this further, even on the hypervisors?
Maybe. It depends on the MSR. I don't know. You might do some research on that and find out.
Yeah, and I've got also a question about the because you are changing the L-star MSR so that, if I understood correctly, you can then specify like what will be the syscall handler, right?
Mm-hmm.
But how do you like place your executable code in the kernel, right. or is there like no SMAP or SMAP or things like that on Windows?
Right. So this is actually a good question. So you don't have SMAP with A. You do have SMAP with E. So you cannot actually let the kernel just change into user space code and it will just run it as in kernel context. So basically, what I did there, I use a really cool open source project called MSR exec, which let you just do that. So basically, you are creating a ROP on the stack to disable the mitigation, the SMAP mitigation. Then you just jump to your user mode function and everything's
okay. Very nice. Thank you.
Okay. So regarding the previous question, here.
All right.
There's a really good blog post about secure kernel PageGuard, which runs in the Hyper-V mitigation, and it explains in detail how it works, what are the extents, etc. So it describes all the MSRs, which are handled, which are not, and stuff. Because there's much more. It protects core of the Windows kernel, so you cannot hijack some of the pages and more like that.
Mm-hmm. You're talking about the one that Yarden Shafir wrote, right?
Probably, yes.
Yeah. Mm-hmm.
Hello, thank you. Very nice talk. I have a little question. So you said several times developers have a lot to know about. Mm-hmm. How is the documentation?
It's pretty good. The major problem here was that this codebase actually written in the early 2000s, so and it's still being used today. Actually this was written as a proof of concept, not a production driver. For some reason, it's still being used as a production driver. No why? So it created a lot of problems, really.
Any questions? Maybe that's rather a comment. Maybe someone should create an AV product where they would try to disassemble the drivers, like custom drivers, and try to like find out those bugs and block them.
So Microsoft tried to do some of this, and also some of the variation of this driver is actually in the block list of the driver that should not be loaded. So Defender should block this one, but there are too many variations of this driver, and they always resign those. So basically, you cannot find all the different variation, as long as you're not really putting a lot of effort into that. And unfortunately, nobody did it by today.
Other questions?
Right.
All right. So thank you again.
Thank you.
Go
Thank you, guys.
Round of applause.